Hey, how you doing? So we've got one more problem to do today, and it's a simple truss. So it's a pin-jointed truss, and it's supporting a single externally applied force, a point load at point A of 1,000 newtons, and shown in the diagram. So basically, a bunch of bays of 2 meters each, a vertical height of 2 meters. And we were asking three different questions. The first one, determine the reactions. Okay, that makes sense. Determine the internal axial forces, and specifically in members BC, GC, and GF. So kind of in the middle of the truss. And then determine the stresses in these members. Okay, so we need to know the area. And I've actually gone ahead and calculated the area. They're all the same area. So I did that in a preliminary calculation. So that's shown here on the slide. And all members are tubes with the inner and outer diameter of 16 and 80 millimeters respectively. And so those were used in calculating that area. And so we should be good to go. So I've already set up for a free body diagram. Let me just label it here. We have free body diagram. And let's put our loads on. So we have an externally applied load at point A. And that's 1,000 Newton. And then let's add our reactions. And so I'm just going to draw. So we have an X and a Y at our pin at D. So I'm going to draw that in here. Reaction at D in the X. Reaction at D in the Y. And reaction at E in the X. And it's a roller, so it's obviously got to go perpendicular. That's why I know it's horizontal and not vertical, because of the way the roller is configured, right? So it's got to go perpendicular to that line. So that's in here. So that's why I've done that. And the other thing that I want to do is I want to get a feel for what is our ratio of these members. And so if it's 2 and 2, I'm going to use Pythagorean theorem and figure out that our length is then 2.83. And that's also the ratio that the internal forces are going to have to take so that they line up with the members. So that's useful information to have. And I guess we're ready to solve for the reactions. So let's do that. Solve for reactions. And I'm going to do the sum of the moments, and I'll do it about D because that'll take two of the unknowns out of the way. So I'm guaranteed to be able to solve directly for REX. So let's do that. Sum of the moments about D equal to 0. I'm going to choose clockwise as positive. And so what do we have? We have REX, and it's trying to turn it clockwise, so it's positive, and it has a perpendicular distance of 2 meters. So we'll put that there, and then we have the 1 kilonewton, or the 1,000 newtons off at point A. So it's trying to turn it counterclockwise, so we have 1 kilonewton at point A, and its perpendicular distance then would actually be the full 6 meters in length to get out to it. So 6 meters, and that's about all we wrote there. And so we can solve for REX, and we get a value of 3 kilonewtons. And I'm going to put that over here, 3 kilonewtons. And now I'm just going to do sum of the forces in the X direction is equal to 0. And so we have minus RDX minus REX, and this is 3 kilonewtons. And so we get R, sorry, just a minute. How did I do that? RDX. So RDX is equal to negative 3 kilonewtons, and that just indicates that the arrow direction that we assumed when we drew our free body diagram is actually opposite. So we'll just put that in as a negative 3 kilonewtons up here. And the last one that we have to do is we have to do sum of the forces in the y direction is equal to 0. And so we have a negative 1 kilonewton at A and a plus r dy. And so we get r dy is equal to 1 kilonewton. And again, I will transfer that over here as 1 kilonewton. So that's it. We've solved for all of our reactions, so reasonably happy there. So that's part A, and so now we have to look at part B, which is to determine the internal axial forces in members BC, GC, and GF. Now, the two methods that we've talked about on how to do this, we can do the method of joints or we can do the method of sections. Because we're not solving for the entire truss and I don't want to start at one end just to get all the way to the middle, I can use the method of sections and it'll probably save me some time. And so I'm going to draw a section just down here, kind of just to the right of BG. And that means I can do the method of sections, partial free body diagram, and solve directly for those three internal forces. So I'm just going to create my partial free body diagram. Okay, so I've drawn in the left-hand side. I figure that's going to be the easiest one to do with the least number of forces applied and the distances are obvious. And so now what I need to do is I need to add the externally applied load, and that's 1 kilonewton. And now I need to do the internal forces, and so we have a force BC. And so I'm going to draw it in that direction as if that was tension in BC. So if BC is in tension, it's pulling on the section or on the joint. So that would be FBC. And then I'm going to do the same thing for the force in GF. And the force GC. Is right there. And so that's our partial free body diagram. I'm happy with that. And so now I can go ahead and I'm just going to say method of sections. And basically we're solving for internal forces. Okay, so I have, if I look at my partial free body diagram, I'm trying to see what I can most easily solve for directly. I see I have a single vertical component in GC, no other vertical components. So I can go ahead and I can do sum of the forces in the y direction is equal to 0. And I'm going to use my ratios. So if I want to do this, so 2 over 2.83, so that would be the vertical component of FCG, so multiplied by FCG, and that's positive up, so that's good, and then less the 1 kilonewton applied, and so we're able to directly solve FCG as equal to 1.415 kilonewtons. And I'm just going to write that in here, 1.415 kilonewtons. We got a positive value, so we're happy there. We know it's in tension. And so I should write that down. So let's say tension. And now let's do the sum of the moments, and I'm going to choose to do the sum of the moments about G. is equal to 0. That way both FGC and FGF will disappear, and we're only going to get FBC is the only unknown. Again, I'll choose positive as clockwise, and that will be equal to our force FBC multiplied by the perpendicular distance to it from G, and that would be 2 meters. And then we have our 1 kilonewton. It's trying to pull it counterclockwise, so it's a negative 1 kilonewton, and it also has a perpendicular distance from G of 2 meters. And so we're able to solve for FBC is equal to 1 kilonewton. And again, because it's positive, we know that that's in tension. And I'm going to go ahead and write that in here, 1.0 kilonewtons. As well, tension. And our last equation of equilibrium then will get us the other one. Sum of the forces in the x direction is equal to 0. And what do we have? We have FBC going to the right. That's got a value of 1 kilonewton plus our x component of GC. So again, that's the same ratio, 2 to 2.83 of FGC. And it's going to the right, so it's positive. And this value we know is 1.4415 kilonewtons. And then we have FGF, and it's also going to the right, so plus FGF. We don't know that, it's our only unknown, so let's isolate on that unknown, FGF, and we'll solve for it, and we get a value of negative 2 kilonewtons. Because it's negative, we know it's in compression because we drew it in as if it was in tension. And let's label that up here as 2.0 kilonewtons in compression. And so having done the internal forces, that resolves part B of the problem. We just have to get the stresses. And so let's do that right over here. We got lots of room. Internal stresses. And we can do our stress at CG. That's equal to our internal force in CG divided by our area. All of the areas are the same, so I don't need to indicate those. And CG, we determined was 1,415 newtons divided by the area of 2199 millimeters squared, and that's equal to 0.643 megapascals. Because the force is in tension, this is also in tension. And then we can do our sigma of BC is equal to our force BC divided by our area. And so the force in this case was 1,000 newtons divided by 2199 millimeters squared equals 0.455 megapascals, and also in tension. I was going to say the stresses are really low in this particular truss, not overly loaded at all. GF equal to PGF divided by A, and that's equal to our negative 2,000 newtons divided by our area of 2199 millimeters squared, and that gets us a value of 0.910 megapascals. That was negative, and that is compression. And that resolves part C. So it's a fairly straightforward truss. I think walking through the free body diagram, get the external reactions. It's always the best place to start. And then recognizing that we can save ourselves a little bit of time by using the method of sections to solve directly for the three internal loads and stresses that were asked for, and not pursuing the method of joints. You can get there by the method of joints. You're just going to take you a little bit longer, a couple more calculations. So with that, I'm pretty happy, and I hope you are too. And we'll see you at the next one.